Okay, so our next topic is going to be alkenes and alkynes. So alkenes are hydrocarbons that contain carbon-carbon double bonds. So far we've had only molecules that have had carbon-carbon single bonds. This is going to change that. Let's take a look at our pentane example again. So the pentane molecule has got all carbon-carbon single bonds. So this is an alkane. If I want to turn it into an alkene, I need to turn at least one of these into a carbon-carbon double bond. So what I need to do with the model kit is take out one of these single bonds, and the double bonds can be formed by using two of these springs. But in order to form a double bond, I need two holes available on each of the carbons, right? And right now, carbon has got one hole available from the single bond that I just took out, but it doesn't have enough room in its bonding capacity to form the double bond. So kind of like with the cyclic compound, in order to make the double bond work, I'm going to have to take out a pair of hydrogens. This carbon's got to lose one hydrogen, this carbon's got to lose one hydrogen too, in order to make room for the double bond. So if I get rid of those guys, then I can put the second spring in, and that's going to allow me to make a carbon-carbon double bond. So now instead of pentane, this molecule would be called pentene. And because it's lost a pair of hydrogens, it has 5 carbons, but only 10 hydrogens. So it's got a different general formula than the alkane did. In fact, the general formula is going to match the Cyclo Alkene. So the general formula for these is going to be the same as Cyclo Alkene. So if they're CN, they will be H2N, twice the number of hydrogens as they have carbons. So an example of this would be pentene, like we just drew. Now, if we want to make our, let's put a pentane in first. So here's our pentane, and then in order to form a double bond, we had to get rid of a pair of hydrogens. So each of these carbons would only have a single hydrogen there. Let's put that second bond back in. So this would then be pentene. What we're going to find is we're going to have to number our carbons and identify the location of the multiple bond, which we'll get to in a minute, but this one starts on carbon number 2. So this name would actually be pent 2 ene would be the correct name, which would show me where the double bond is as well. Now these molecules are going to be more reactive than alkanes. And the reason why they're more reactive than alkanes is because if we look at the shape of the molecule, remember it's got this double bond sitting over here. So the double bond has got extra electrons that are kind of sitting around the bond over here. And those electrons are going to be an excellent site where other molecules can come in and react with this molecule. And that's going to be then make this a really attractive site for another molecule to come in and to interact with. Second reason why they're more reactive is these hydrogens actually block other molecules from coming in and interacting with the atom here, or interacting with the electrons here and doing a chemical reaction with it. And when we took off the pair of hydrogens and shifted these ones over here, we opened up space, which is going to allow for an easier access from things that are going to want to attack and bond and like react with this molecule here. Next little bit here is going to be on alkynes. Now alkynes are going to be kind of similar to alkenes, except that instead of having carbon-carbon double bonds, they have carbon-carbon triple bonds. And it's somewhat easy to remember alkanes, alkenes, alkynes. They're only different by one letter, which is a little tricky, but the 3 letters are in alphabetical order as you add more double bonds, or as you add more multiple bonds to it. So the alkanes comes first, has an A, alkenes is second, It's got double bonds, and then alkynes would come third, and they've got the triple bonds. So let's look at how we make an alkyne. So I'll come back to my pentene here, right? It's pentene because we've got a double bond in it. If I want to turn this into pentyne, I need to turn this double bond into a triple bond. I can do that by adding another spring, but I need room for the spring to go, right? I need another hole, I need another opening in this carbon and this carbon's bonding capacity. So what do I have to do? I have to take off another pair of hydrogens. This hydrogen and this hydrogen are both going to need to come out. So let's take those hydrogens out, and then what I can do is I can put the third bond in like this. It's going to make a triple bond, which is going to make an alkyne. So now instead of pentane or pentene, this molecule would be called pentyne. It's only a little bit coincidental that it looks like a wiener dog. Okay, I may have been home by myself for too long. Now, alkynes are going to be more reactive than alkenes or alkanes for kind of the same reason that alkenes are more reactive than alkanes. The alkene has got some of these extra electrons sitting on top, and we had removed hydrogens to make it easier for something to come in and attack. Well, this is even more the case. I've got more extra electrons that are part of this multiple bond that are sitting out here. Those are really attractive for somebody to come in and react with. Another molecule can come in, or another atom can come in and react with this one. And then we've also removed even more hydrogens, so there's even more room kind of available. It's not crowded. It's easy for something to come in and attack this wiener dog anywhere around its middle. And then finally, before I go back to the notes, when we do the general formula, we had to take off another pair of hydrogens. So this guy has got 5 carbons still, but now instead of 10 hydrogens, it's got only 8. We had to take off an extra 2. So the general formula is going to be CnH2n minus 2, because we have to take off an extra pair. So my general formula then is, like we said, CnH2n minus 2. We'll maybe put a little reminder here on the alkenes that this is the same general formula as Cyclo Alkenes. Cyclo Alkanes have the same general formula as a straight chain alkene. Now for the alkyne, let's give ourselves an example. So we did pentyne, so we turned our pentene into a pentyne. So we had to take off this hydrogen, right? That guy we had to remove in order to make enough space to have my triple bond here. So here's my carbon-carbon triple bond. And then this carbon also doesn't have any hydrogens on it because it doesn't have room in its bonding capacity. So then the next one in the chain has got 2, and the last one has got 3. So I still here have 1, 2, 3, 4, 5 carbons in the chain. And the triple bond is between carbons 2 and carbon 3. So that's where I'm going to draw it in. This guy will be called pent-2-ine. Ine specifying that it's an alkyne. Now, a couple of notes about naming alkynes is the parent chain has to contain the multiple bond, even if it isn't the longest chain. So what we're concerned about with alkanes is that we find the longest chain. Well, here it's going to be the longest chain that contains the multiple bond. It has to have the multiple bond in it. And then numbering, the multiple bond is going to take priority over alkyl groups. So we had to number before at the side that was closest to the multiple bond, or sorry, closest to the first group. Now we don't care about that. We're going to start numbering from the side that's closest to the multiple bond. And then the locant goes before the ene or the ine in the ending, like we did before. So let's take a look at an example. So we have 2 here. These guys have been numbered for you already. So we're starting at the side closest to the multiple bond. Here's my backbone. It's got 4 carbons in it. And then I have a double bond between carbons 1 and 2. So but1-ene is going to be the name of the molecule because we always identify the multiple bond with where it starts. So the first carbon that it's on. So this guy would be but1-ene. This molecule over here has the double bond starting at carbon 2. So this is good. This guy is going to be called but2-ene. Then if we have some branches, the branches are going to get numbered, or the branches are going to get named according to the same rules. They kind of go out in front, but you have to remember that the multiple bond is going to take priority in terms of your numbering. So for my first molecule here, I'd be tempted to start numbering at this side because it's closest to the branch, but that's wrong. I have to start numbering it at this side because it's closest to the multiple bond. So I'd number this guy 1, 2, 3, 4 from right to left. So this is my backbone. It's got a double bond, and I've got a methyl group hanging off of it here. So this molecule is going to be called 3-methyl, and then the backbone is a but1-ene. For my second one down here, find the longest backbone that contains the multiple bond. Multiple bond is here. I don't want to lose sight of it. This is then going to be a branch. So it's another methyl branch. And then I have to start numbering at the side closest to the double bond. So 1, 2, 3, 4, 5, 6. So it's going to be a hexene backbone with a methyl on carbon 5. So this guy will be called 5-methyl hex 2-ene, because the double bond starts on carbon 2. Then for line diagrams, you just have to keep track of where the carbons are, right? There's a carbon at each point here, so you can kind of draw them on as you're getting started. There would be carbons here, 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 here. So that means that this is my parent chain, and this guy is a group. So I've got a methyl group on carbon 3. So this guy will be called 3-methyl. And then it's a but1-ene backbone. And then for this guy here, right, here's my parent chain. It's got to contain the multiple bond. That means that this carbon is a branch, and the rest of these carbons are part of the backbone. So 1, 2, 3, 4, 5, 6 are in the backbone. Methyl on carbon 5, so 5-methyl hex 2-ene. Alkynes will work the same way, right? Except instead of an ene ending, they get an ine ending. So I find the longest backbone, look for branches, start numbering at the side closest to the multiple bond. So 1, 2, 3, 4, 5. So this is a pentyne backbone. It's got a methyl on carbon 4. So 4-methyl pent 2-ine. Then when you're drawing them out, just watch and make sure if you're drawing an alkyne, you're taking off enough hydrogens that you're not going over carbon's bonding capacity. So maybe I'll just do the first one here, 4-methyl pent 1-ine. So I'm going to put the backbone in first. It's got 5 carbons, 3, 4, 5. Let's number them. 1, 2, 3, 4, 5. Then I've got a triple bond starting at carbon 1. So this first one is going to be a triple bond. The rest are going to be single bonds. And I've got a methyl on carbon 4. And it's asking for a condensed structural diagram. So that means my hydrogens are going in line here. CH3, CH3, CH, C, H2. This carbon doesn't get any hydrogens because its bonding capacity is already full. This one gets 1 because it's got 1 space left in its bonding capacity. Dimethyl-but-1-ine. You notice that we don't have a locant here. We don't have a number telling us where to put the methyls. That's because they can only go in one place. So maybe pause your video for a second here. See if you can figure out how to draw dimethyl-but-1-ine. And then I'll put it up here in a minute. You can resume and see what it looks like. So hopefully you tried it. I drew out this much of it, and I'll just show you why we don't need a locant. So I can't have the methyls be on this carbon here because its bonding capacity is full. It can't go on either of the terminal carbons because that would extend the backbone, and it wouldn't be a butane backbone anymore. So the only place that the methyls can go is on this carbon right here. So I'd put my methyls here. And this guy gets 3 hydrogens, and then just watch both of these 2 carbons in the middle. They don't get any hydrogens because they don't have room in their bonding capacity for any of them. And finally, when we talk about multiple bonds, we will talk about the idea of saturation. So alkanes are considered to be saturated because they contain only single carbon-carbon bonds. So they're saturated with hydrogens. They have the maximum number of hydrogens that they can possibly have. In order to form an alkene or an alkyne, you have to remove hydrogens, which makes them unsaturated. So alkenes and alkynes are considered to be unsaturated because you have to remove hydrogens in order to form them. Now, last little bit here is you can also have a cyclo alkene and a cyclo alkane, right? Just like you can have a cyclo alkyne, just like you can have a cyclo alkane. And when you're building those guys, you have to take off some hydrogens to make the multiple bond. Then you have to take off another pair of hydrogens in order to make a ring. So with the cyclo alkene, for its general formula, our straight chain alkene would have been CnH2n. But in order to make it cyclic, you have to take off an extra pair of hydrogens. So it'll be 2n minus 2. And for a cycloalkyne, you have to take off the 2 to make it a straight chain alkyne. And then you have to take off an extra pair to make it cyclic. So its general formula will be CnH2n minus 4. Cycloalkynes are not particularly common. Now, when you're naming these things, you just have to watch your numbering because you have to start numbering across the multiple bond, and then you have to go towards the first branch. So towards the first group. Towards the first group or branch. So in this example here, I have to start, this is a cyclohexene backbone, right? It's got 6 carbons and they're in a ring. I have to start numbering across this double bond, and I have to make sure that when I come out of it, I'll be going towards my branch. So I have to start here with this is carbon 1, this is carbon 2, so that this guy gets carbon 3, 4, 5, and 6. So the name then would be 3-methyl, because I've got a methyl on carbon 3. And then it's a cyclohexene backbone. I don't need the locant for the cyclohexene because we know you would have started numbering across the double bond. So maybe pause your video and try this guy and see if you can get him named. So I see two groups here, 1, 2. I need to start numbering across the double bond towards the first group. So I'll go around like this. The double bond always has to fall between carbons 1 and 2 in order to be properly following my rules. Now I've got a methyl on carbon 2, I've got a methyl on carbon 3, so the name will be 2, 3 dimethyl. And then this guy is a cyclopentene ring. And again, I don't need a locant because we would assume that the double bond is between carbons 1 and 2. So dimethyl, cyclopentene.